Hello, hello. Yes, just the mic for the people remotely. Thank you everyone for coming. We're all here for Sangwoon today. And before we start, just like a few procedural notes, right? So first, Sangwoon will present for about 45 minutes. And then after that, we'll have an open round of questions from anyone in the audience. And then after that, if the faculty ask for it, we can have a round of questions, just close the session. After that, the committee will deliberate. And after that, we'll invite everyone else back into the room to announce the decision of the committee. And whatever happens, then in 5314, we'll have a celebration because today is a day of celebration, the celebration that you made it to here, to this moment, right? Right now.
Not passing.
Just you made it to this moment. That's what we need to celebrate. So I want to start thanking everyone in the room and especially the committee for making it to have Professor Sanbe Kim and Pulkit Agrawal and especially Professor John Leonard, who took a 6 a.m. flight this morning all the way from the other coast to make it to be on time here. Thank you for making the effort. It makes a difference. Thank you. So Sangwoon. Sangwoon started his grad studies here in Meki, working with Professor Brian Anthony. And around fall 2020, right in the middle of the pandemic, he joined our lab to work in robotic manipulation. And even through all the challenges, the pandemic, all the things that were changing groups, Sangwoon has shown to be a rock and has shown to be able to maintain a laser focus attention to a problem that he got interested in. And over the last 4 years, he has shown relentless progress towards more complex and more complete versions of that problem, which is actually a problem that I hold very dearly to myself. It's a problem of how do you manipulate, how do you understand, and how do you control the interaction between an object you're holding and the environment. May it be tool use, may it be because you want to reorient or manipulate the object you're holding. So you'll see that Sangwoon has made significant progress along that problem. So this is a journey in which I've learned a lot from you, Sangwoon. So thank you for that. And it's a journey that I've enjoyed quite a lot. So, and I hope that you do too today. So thank you very much for coming today, Sangwoon. The stage is yours.
All right. Thank you, Alberto, for a very generous introduction. And thank you, everyone, for joining my thesis presentation today. So today, the title of my thesis is TEXterity, which stands for Tactile Extrinsic deXterity. But before I explain what this actually even means, I'd like to talk a bit about the current status of the robotics research. So it's only been several years since we've seen the success of the AlphaGo, but we've already seen so many AI-enabled breakthroughs that not only works in the video games, but also actually works in the physical world. For example, we've seen the legged robots that can perform parkours in the wild, and we've seen the AI pilots that can beat the human champions in the drone racing. And I just named a few of them, and there's just so many AI-enabled breakthroughs in robotics and autonomy that can actually achieve human-level performance in various tasks. However, when it comes to the robotic manipulation, I think it's a bit of a different story. I personally believe that robotic manipulation is lagged behind compared to the other areas of robotics, such as locomotion or perception. For example, until very recently, the mainstream research community has actually focused mostly on pick-and-place types of tasks, which involves relatively simpler physics. For example, the recent emergence of large language models or vision language models show some great promises for generalizable manipulation. However, I believe that these models have very inherent limitations when it comes to reasoning about the complex physical interactions. And I think this is mainly because these models are not grounded to the physical reality. So for example, these models today can do tasks like passing an apple to a human, or moving this Coke can to this Taylor Swift photo. However, these models today still suffers to do tasks like peeling an apple or opening a Coke can, which involves much more careful reasoning about physical contact interactions. And of course, our fellow roboticists has put a lot of effort into solving this problem to enable physics-aware robotic intelligence that can reason more carefully about the contact interactions. So for example, one very promising approach would be modeling all those complex interactions in simulation and then learning a policy or action inside that simulation. And also one very promising approach would be showing some demonstrations from human and then making robots to learn through the imitation learning to clone the behavior of the humans. And of course, there's model-based planning or model-based optimization to plan for the complex sequence of motion in the context-rich manipulation task. And I genuinely believe that all these approaches are very promising. However, they're still far way to go, and then they're still far yet below the human level. So that being said, the point that I'm trying to make today, make in this slide, is that regardless of which approach that we take, I believe that following statement is always going to be held, which is that we need to better understand and leverage the physical contact interactions. So then the following question will be, how can we better embrace those physical contact interactions? Of course, we should first sense it better and then understand them better and act upon it in a more clever way. And another following question will be then, what signals should we sense? So in order to figure that out, let me look back at one of the examples that I showed you in the previous slide. So in this work, which does the sim-to-real transfer of this assembly line task, what they report is that they report the major failure mode was due to the slip between the finger and the object. And I'm pretty sure if the same task was done by human, us human can definitely sense the slip on our finger, and we can easily recover from those failures. However, these robots weren't able to do so because these robots only relied on the vision data from the external camera. And this is just another example of showing how much us humans rely on the tactile sensing on our fingertip. So what is happening in this video is that this person has actually numbed her own finger, and therefore she suffers to put fire on this match. So the point that I'm trying to make here is that as humans heavily rely on these tactile stimuli to feel and act in various tasks in our daily lives. And that's the reason why I strongly believe that embodying these abilities of utilizing and leveraging the tactile sensing is going to be critical in achieving human-level dexterity in the future of robotics research. So in order to fully embrace the tactile information, as I mentioned, we should first sense them better, understand it better, and act upon it more cleverly. And to understand the tactile information more better, there has been a lot of work that focuses on the estimation and simulation of those tactile information. And in the another direction, there has been also work that more focuses on the control aspect of the problem. That said, I believe that in order to fully embrace the tactile information better, then I believe that we should concurrently tackle those two directions simultaneously. And that's the direction that I would like to pursue. And I would like to pursue that direction by achieving TEXterity. So what is TEXterity? What does it even mean? So tactile extrinsic dexterity, what does it even mean? So let's think of an example scenario where you're grasping an object and you're also interacting with some external environment. In this case, you have a contact between the gripper and the object, which we call intrinsic contact. And we also have a contact between the object and the environment, which we call it extrinsic contact. And these kind of, if you think about it, these kind of extrinsic contact is very common and prevalent in our daily lives. So whenever we want to use a screwdriver and when we want to load the dish to the dishwasher, we always engage with these extrinsic contact, and we even further leverage those extrinsic contact to enhance our dexterity. So what I would like to do with TEXterity is that we would like to do these kind of do these kind of tasks with tactile sensing. So in other words, with TEXterity, we would like to use tactile sensing to interact with the external environment through the extrinsic contact, and then further leverage that interaction to do more dexterous manipulation tasks. So that's what TEXterity means, and that's the objective that we would like to study today. So we now have our objective, we now have our goal. So I would like to visit what are the main challenges of embodying those kind of tactile intelligence to the robot. Of course, there are many challenges, but one thing I would like to point out is the challenge of interpretability. So there are so many different tactile sensors, but let's focus on this vision-based tactile sensor, for example. So this sensor is called gel sight. And what it does is that it tries to observe the deformation on its finger through this high-resolution tactile image. And because this raw observation is high-resolution image, it is still unclear on how we should consume this raw data as some sort of interpretable input to the robot. And there's also a challenge of observability. So by its nature, tactile sensing is a local observation, which means that it can only sense the part where it is directly touching, but it cannot sense the part where it is not touching. In other words, extrinsic contact. And the next challenge that I'd like to highlight is the challenge of added uncertainty. So when you observe something with the tactile sensing, then you gain information. So that is a good thing because you gain information, but at the same time, you're adding uncertainty through the physical interactions. So for example, when you push this box with your finger, you gain information through tactile sensing. However, at the same time, you're adding uncertainty because this box could either slide to the left or either slide to the right. So it is very important to think about how we can handle these kind of augmented uncertainty introduced by the physical interactions. So with those challenges in mind, throughout 4 years of my PhD, I asked myself a question. I asked myself a question on how we can address those challenges. And these are the four projects that I tried to solve throughout my PhD journey. So this is what I'm going to walk you through today. So let's start with the first one. So in the first project, since it was a very early stage project, first thing that we wanted to do was that we wanted to justify whether tactile sensing is actually useful. So in order to figure that out, what we done was that we trained a end-to-end reinforcement learning policy to train for this peg in-hole insertion task, where the inputs are just this stream of tactile images, and the output is the post-correction to compensate for the misalignment between the peg and the hole. It worked out pretty well, to some extent. However, it came with a very severe limitation, which is that the amount of time and effort that we had to put in to train a single policy was just unreasonable. So we had to spend like days and days to collect the real data, to train a single model, and we had to repeat that process whenever we make any modification to the model. So at that point, I thought this approach might not be sustainable, so I wanted to find a more efficient way of solving this problem. So that's why I started the second project. So in this second project, the question that I asked myself was, okay, I know that tactile sensing is useful, but how can we exploit the tactile sensing more efficiently? So in order to tackle that problem, the approach that I took was decomposing the task into two different parts, rather than taking the end-to-end approach. So first part is taking the abstraction from the state, and the second part is using that abstraction as an input to the policy. So let me explain what that means. After I hide this panel. Yeah, so let me explain what that means. So this is how I decompose a problem into this bi-level task, bi-level problem. So the first part is the active extrinsic context sensing. So the first part is the active extrinsic context sensing module, which extracts the state abstraction in forms of extrinsic content location. And the second part is the insertion policy, which takes that contact line as an input and outputs the post correction to compensate for the misalignment. So let's first look into this active extrinsic context sensing module first. So what this module is trying to do now is that it tries to move around the object. It tries to wiggle around the object while maintaining stable contact between the object and the hole. And by doing so, what we like to do is we would like to localize this extrinsic contact line where the object can pivot around. And if you think about it, this extrinsic contact line is actually a very efficient abstraction that represents the state of the misalignment between the peg and the hole. So the idea is that we would like to use this extrinsic contact line as an input to the insertion policy. So our insertion policy takes that as an input and outputs the post correction at the next step. So if you look at this figure, so this figure is a top-down view of the scene. So if you look at this figure, we see the current pose in blue and also the next pose as an action as green. So, and then based on that action, what we do is our robot corrects its pose, and then it tries another attempt to find a contact line. And then it just repeats this process over and over again until it managed to insert the object into the hole. So it finds this contact line, and then we again compute the action, and then based on that action, we correct its pose, and then tries another iteration, and find this contact line, computes the action again, and then you finally manage to insert the object into the hole. So that's briefly how it works, but let's look into it a little bit more detail to see what is going on. So first we have this raw tactile images, and then what we do next is that we convert these raw tactile images to this rigid body relative pose between the gripper and the object. And then we fuse these information along with the gripper pose from the robot proprioception. So to fuse this information, we used a framework called the factor graph. So if you don't know what is factor graph, don't worry, I'm going to explain it in the later slide, but we used a framework called the factor graph for now. And then what this factor graph does is that it tries to compute a line that maintains stationary throughout the motion in order to find this extrinsic contact line. And then we also have a very simple controller to control the contact state to be stable so that the object does not slip over the hole or also lose contact with the hole. So we also have that very simple controller. And with those two modules, we are able to localize this contact line, which goes into the reinforcement learning policy. And then one thing to note here is that our reinforcement learning policy has a recurrent architecture, so therefore it can consider not only the current attempt, but also the history of the previous attempts. And then we can insert the object into the hole. So that's what happens during the testing time, but now you might be wondering, how do we train those reinforcement learning models? So the key insight here is that since we use extremely simple abstraction, which is extrinsic contact line, we can train the policy completely in a very simple simulation. And this is how easy the simulation is. So it's nothing like Mojoko or it's nothing like Isaac Gym, but it's just a piece of paper. I mean, not a piece of paper, but just a 2D plane with some random shape of holes and objects drawn on top of it. So what we do is we draw any shape of the hole that we would like to simulate, and then we draw any shape of the object that we would like to simulate. And then what we do is we just move around that object based on the pose correction that we get from the policy as an action. And then what we do is that we just find this intersecting line between the object and the hole. And if you think about it, this intersecting line is actually equivalent to the extrinsic contact line if this was done in the real experiments. So therefore, we can just train our policy completely inside this very simple simulation, and we can just directly deploy to the real world without any further training. And by deploying the policy to the real world, we were able to insert various unknown shape of the objects to various unknown shape of the holes. And one thing worth highlighting is that it actually significantly outperformed the previous work. And this is worth highlighting because in the previous work, we had to collect hours and hours, days and days of data to train a policy. However, in this current work, we did not have to collect any real data to train the policy, but we were still able to outperform the previous method. So I would like to highlight this result. So that was the second part. So that's what I did in the second project. So what I done was, in order to make our algorithms more efficient, I took the abstraction or representation in forms of extrinsic contact, and it worked out really well. However, it came with a lot of different limitations. So one of the limitations was that although we have a very simple controller, that controller was just a very simple heuristic controller. So in other words, it was able to only reason over just a single types of contact formation. And also, it wasn't able to reason carefully about what is the contact force. And therefore, what's going to happen if we deploy the same controller to a different contact formation? The robot is just going to lose its control and then slip all over the surface. And that was what we wanted to solve in the third problem. So in the third problem, the question was, okay, we now know that extrinsic contact is an efficient representation, but how can we reason more carefully while maintaining control about those extrinsic contact? So in other words, we wanted our algorithm to be able to handle multiple different contact formations. And also, we wanted our controller to reason more carefully about the contact forces. And also, we wanted to do all those things while the estimation is uncertain. So in other words, we had to solve the estimation and control problem simultaneously. So let's go back to this example of where you want to manipulate this unknown grasped object on top of this freestanding vertical rods using the tactile sensing. So in order to properly manipulate this object while maintaining control, so in this case, it will be not toppling down this bar, we need to carefully reason about what are the contact states. So such as, what is the displacement due to the deformation on its finger, and what is the wrench exerted on the finger, and what is the location of the extrinsic contact, and what's the contact force there, and what's the contact mode, and what's the contact formation. And in order to solve this problem, what we came up with the simultaneous estimator controller. And by solving those estimation and control problem at the same time, we were able to generate synergies. So if you think about it, if we have a good control of the system, then in this case, it will be the bar not moving around, but just maintaining stable. And in that case, we're going to be able to get a better estimation. And by using that better estimation, we can again further improve our control. So therefore, there was this synergistic loop going on by solving the problem of estimation and control problem at the same time. So this just shows a video of how the algorithm works in the video. So as I mentioned, our algorithm is capable of estimating the contact state while controlling it. So for example, if you look at this figure, you can see that the confidence ellipsoid on this extrinsic contact location tends to shrink as we fuse in more and more information while maintaining control. And it can also detect the transition in this contact formation from the point contact to line contact, and it can eventually place this object on top of these freestanding vertical rods while not toppling down any of these vertical bars. So how does this thing work? So I would like to briefly explain how this thing is actually working. So first thing we do is we incorporate the measurements and constraints. So the measurements include the tactile sensing from the sensors and force kinematics from the robot. And we also incorporate some geometric constraints, such as the point of the contact should maintain stationary throughout the motion. And we also incorporate some physical constraints, such as there should be no torque exerted at the point of the point contact. So we incorporate those kind of measurements and constraints, and we also incorporate our control objective that needs to be satisfied. So the control objective that we imposed was that we want to minimize the deformation on the sensor finger while not losing the contact at the extrinsic contact. And we also wanted to minimize the tangential force at the extrinsic contact so the bar does not move around. And we also incorporate which direction we would like to move around the object. And what our algorithm does is that it incorporates all of these informations and comes up with some estimation of the state along with the motion plan to control the contact state and at the same time satisfy the control objectives. And in contrast, if we use a controller from the previous method, which does not reason carefully about the contact state, the rod just tumbles down due to the excessive tangential forces. So this shows an architecture of our framework. So again, similar to the previous work, we use a factor graph. We use a framework called the factor graph. And if you don't know what is factor graph, I think it's a good time to introduce what it is. So the factor graph is a framework that can fuse various sources of information and can come up and can compute a state that best represents those information. And it can do that by minimizing the total factor loss, which we call it energy function. And what's cool about this factor graph is that each of the measurements, constraints, and control objectives that I introduced in the previous slide, each of them can be formulated as a factor. And it means that we can solve the estimation and control problem jointly within this single factor graph by minimizing the energy function. So if you look at this factor graph, we have a timeline from the initial time to current time, and also towards the end of the control time horizon. So from the initial time to current time, we incorporate the factors that are related to the estimation, such as measurements and constraints. And from the current time to the end of the time horizon, we incorporate the factors that are related to control, such as control objectives. And by minimizing the total energy function of this entire factor graph, we can come up with the state estimation of the contact state. And along with that, we can also come up with the motion plan to control those contact state and also satisfy the control objectives that we imposed. And then this motion plan then can be sent to the robot, just like what we do in the model predictive controller. And this is just another example of placing this rectangular object on top of this very slippery surface while very minimal slip on the ground. So we see here the desired and actual rotation. And we also see the tactile deformation on the fingers. And then we also see the estimate of the state, such as contact location, contact line, wrenches, forces, etc. And then it eventually can place this object on top of the slippery surface with very minimal slip. So that's what I did in this third part. So in order to reason more carefully about the extrinsic contact, I solved the estimation and control problem simultaneously within a joint framework. However, of course, it came with a lot of limitation. So one of the limitation was that it is not useful because it does not allow any sliding between the finger and the object. It only allowed a little bit of elastic deformation on its finger while maintaining sticking contact. And also the another limitation was that it does not have any notion of object shape model. So in other words, it does not know what it is grasping or where it is grasping. So it only cares about where's the contact and what's the contact force or what's the contact state. It only cares about those contact states. However, if you think about it, those kind of these information, where is grasping and what is grasping, it's very important to solve many tasks in our daily lives. So for example, imagine when you want to use a screwdriver, you better know where on the screwdriver that you're grasping in order to use it properly. So in other words, this model can reason over the extrinsic contact, but it does not leverage it. So it cannot achieve extrinsic dexterity. So that was the problem that we wanted to extend in my final project. So we wanted to make our algorithm being able to achieve extrinsic dexterity with tactile sensing. In other words, TEXterity. So in other words, what we wanted to do was that we wanted to leverage that extrinsic contact to regrasp the grasped object in its hand by pushing it against the floor or extrinsic environment. And we also wanted a robot being able to estimate where it is grasping and also being able to adjust its grasp to desired grasp or desired configuration. So let's look at several example scenarios in our daily lives where those kind of grasp adjustment is necessary. So for example, when you want to place this chess piece onto the chessboard without colliding with any other pieces, you might want to change your grasp. And what about using Allen key? You might want to change your grasp in order to exert sufficient amount of torque during the screwing motion. And when you want to place this pencil into the holder that is deep into the obstacle, you might want to change the grasp to avoid the collision. And when you use a screwdriver and then you need to do a lot of screwing motion, then you might want to change your grasp in order to make the robot not hit the motion limit during the large screwing motion. And our new upgraded algorithm is actually now capable of handling these situations. So it not only engages with those extrinsic contact, but it now leverages it. It now leverages those extrinsic contact by pushing against it. So we can change this grasp on this Allen key so that we can exert sufficient amount of torque. And then we can change the grasp on this pencil so that we can avoid the collision with these obstacles. And we can also change the grasp on the screwdriver so that it does not hit the motion limit during the large screwing motion. So how does this thing work? So let's focus on the Allen key example. So we first have measurements consisting of tactile images and the gripper pose, pretty much the same as the previous work. And we also have some priors. For example, what is the desired grasp pose that we want? And also some priors on the environment, such as what is the orientation and what is the height of the floor. And we also have some priors on the physics, such as what are the friction parameters. And then we also have our upgraded version of simultaneous tactile estimator controller, consisting of discrete pose estimator and continuous pose estimator controller. So if you look at this discrete pose estimator first, what it does is that it first converts these raw tactile images to this binary contact patch. And this binary contact patch then goes into a module called the tact2pose. And what this tact2pose outputs is that it outputs the single shot probability distribution of relative pose between the gripper and the object within a discretized pose grid. It was long, but yeah, that's what it does. So and this tact2pose module is actually from the previous work in our lab, and it's actually trained in simulation per each object. So once we have that single shot estimate based on that single image, we use a Viterbi algorithm or belief propagation algorithm to filter those estimates so that we have this filtered tactile pose by fusing the images over time. And then it goes into the continuous module. And what this continuous module computes are mainly two things. So one main thing is the past estimate of the object gripper and the contact trajectory. And also it computes the motion plan of the gripper pose to achieve our desired grasp. So if you look into this figure, we see the orange as the current estimate of the object pose, and we see the white as the motion plan for the gripper trajectory to achieve our desired grasp. So you can see that it first tries to pivot the Allen key a little bit and then push it down in order to achieve our desired grasp. And this just to show a video of how it works. So it first tries to pivot the object a little bit, and then it tries to push it down so that we can achieve our desired grasp, and then so that we can do the downstream task more proper way. So that's what it does, and this is the architecture of our framework. So as I mentioned, we first have the discrete pose estimator, which runs the Viterbi algorithm or the belief propagation algorithm. And we also have a part for our upgraded version of continuous pose estimator controller, which is quite similar to that of our previous work. But the main difference is that we incorporated the object shape model to this vector graph, and we also incorporated a factor that explains the sliding dynamics between the finger and the object. So very similar to the previous project, we have a part that accounts for the estimation, and we have a part that accounts for the control. So that's what I did in my final project. So in order to make our algorithm more useful and achieve TEXterity, I incorporated some models. I incorporated the object shape models and also the sliding dynamics model. And now that I've walked you through all 4 projects that I wanted to cover today, I wanted to summarize what were the key findings and insights that I was able to learn while answering each of these questions. So first project was about, the main question was, is tactile sensing actually useful? And our conclusion was, yes, tactile sensing is useful because it provides valuable information about the subtle interactions between the object and the environment. And in the second project, the question was, okay, it's great. Tactile sensing is useful, but how can we exploit those tactile sensing more efficiently? What we done was we used the extrinsic contact as a very efficient representation or abstraction, and it was able to serve as a very efficient, interpretable, and scalable representation that can represent what is going on in the actual context. And the third project, the question was, okay, extrinsic contact is a good representation, but how can we reason more carefully about those extrinsic contact? And what we done was we developed a simultaneous estimator controller. And by solving those 2 problems together, we were able to make our robots enabled to navigate through the uncertainty introduced by the physical interactions. And in the final project, the question was, okay, we have our good algorithm that can reason about the extrinsic contact, but how can we further leverage those algorithms? And what we did was we integrated the models. We integrated the models of object shape models, and also we integrated the models for the sliding physics. So with those learnings and insights in mind, I would like to revisit the challenges that I mentioned in the earlier part of the presentation, and I would like to explain how our learning are related to solving each of these challenges. So first, in order to solve the interpretability challenge, the key takeaway that we got was taking the interpretable abstractions or representations. And in our case, we took context states such as contact location, contact range, and contact mode. And even though I haven't had a chance to explore, but I think one very promising approach would be using some learned features to extract some important information from the tactile observations. And in order to tackle the observability and uncertainty issue, the key approach that we took was fusing the observations and priors over time. So in our case, we fused the information from the tactile images and robot kinematics, and also our intuitions from the physical models. And to handle the challenge of uncertainty introduced by the interaction, we solved the estimation and control problem simultaneously. And by doing so, we were able to maintain the level of uncertainty to a tractable manner. So these were how my learnings are related to the challenges that I explained, that I introduced. But of course, there's still a lot of outstanding challenges that needs to be solved in order to fully embrace the tactile sensing. Of course, there are lots of them, but I would like to point out just a few of them. So the one thing that I would like to point out is the challenge of generalizability. So generalizability can mean a lot of things, but I would like to point out that there are so many different types of tactile sensors. And it is really difficult and important to figure out how can we make our algorithms or data be generalizable over different form factors of tactile sensors. And the another challenge that I'd like to mention is how can we make our algorithms or robots being able to navigate through the unstructured environment. So if you think about the experiments that I've done, all of my experiments were done in a very structured environment, like flat surface, rigid objects. But however, reality isn't like that. We may see cluttered environment, or we may see a deformable object. So I think it's really important to figure out this problem in order to make our algorithms more useful. And I believe that this is a great point where the learning-based method can jump in. So that is going to conclude the technical component of my presentation today. And now I would like to move on to the acknowledgments. So I'd like to first thank my advisor. Yeah, I know this photo is, your best time. Yeah, so. Yeah, so I'd like to thank my advisor, Alberto Rodriguez, because, I mean, I guess most of the people here know that Alberto is a great person and a great advisor. But for me, Alberto didn't, like, what felt for me was that Alberto wasn't just an advisor for me. He was a person who I can always turn to, like, for advice, not only regarding the research discussion, but also all sort of challenges and curveballs that I may face during my journey in my PhD. So yeah, I mean, so I really appreciate for being my advisor and always being there to support me. And yeah, I mean, there's nothing I can say other than just thank you. Just thank you, and thank you again. And I really emphasize with the MIT's Mechie community, Mechie department, that they're losing Alberto to Boston Dynamics. But yeah, I really look forward to the innovations that we'll create in your new venture. And I would like to also thank my dear committee members, Professor John Leonard, Professor Kim Sang-bae, and Professor Pulkit Agrawal. So even if you have a best advisor like Alberto, but if you only discuss your research only with your own advisor, you're very easy to be narrow-sighted. However, these dear committee members provided me with like fresh perspective on my research, and I really appreciate that. So that really helped me improve my research. And also one really important thing is that it really made me think more carefully about how my research can contribute to the research community. So again, thank you for that effort and time that you spent on reviewing my research and then providing invaluable feedbacks. And I would like to thank my lab, the MCube lab. And yeah, as Alberto mentioned at the beginning, I joined this lab in 2020 summer which I think is one of the worst time to join any lab, because I wasn't able to meet with my lab mates due to the COVID. But eventually we were able to like navigate through those challenges as a group. And I really appreciate that mutual support and welcoming from the group. So I would especially like to mention Dr. Siwan Dong for, he's not here, but I would like to thank him because he's been my closest mentor and my first year of my PhD. And I would also like to thank Dr. Neil Doshi for being one of my closest mentor, both at MCube Lab and also during my internship at the Amazon Robotics. And I would also like to thank Ian Taylor for setting up all the research equipments and also providing me relief when like Tony and I are panicking from the broken sensors. And I would also like to thank Antonia Bronars for being the closest collaborator of my final year of my journey. And I really hope all the best for his remaining, her remaining journey. And I would like to thank all the collaborators and sponsors who sponsored me. So I would like to thank the industry sponsors from Mitsubishi Electric and Magna International. And I would also like to thank the people who I get to meet during my time at the internship at the Amazon Robotics. So the collaboration with those industry partners actually helped me to hone my research to an industry standard. And it made me really think about how my research can create real values, not just in the lab, but how my research can create real values. And I would also like to thank my master's advisor, Dr. Brian Anthony, for his support during the first 2 years of my master's journey here at MIT. And I would like to thank my friends and peers who I got privileged to meet here at MIT, Boston, and also in conferences. And I would especially like to thank the people of Korea Grad Student Association, because like living as an alien or as like a foreign person in the United States, that's quite challenging. Some of you might know, but that's quite challenging. But thanks to these people, I was able to feel that like Boston is my home, and they do a lot of stuff together. So they even do things called the qualification exam practice, where they just make someone present and then improve their presentation by providing feedback. And I'm not sure whether that really helped. I mean, it actually helped, but yeah. but it really made me feel that I'm not alone. Like, although I'm like 14 hours flight away from my home, but I'm not alone. So thanks for providing that support. And also one thing I'd like to mention is there are lots of other people who I wasn't able to include in this slide, but that's simply because I don't take many photos. So my apologies. And then I hope we can take photos together today so that you can include the photo in your thesis acknowledgement. Yeah. And yeah, next I would like to thank my family and extended family. So yeah, I mean, I've been living with my parents and family for my entire life before I came here at MIT. And leaving my parents and family and getting on my own feet was quite challenging. But now that I think about it, it must have been even more challenging to my parents and family. And I really appreciate that they stay really determined and then send along endless support across the Pacific Ocean. And I really, really appreciate that. And I really hope they stay healthy and happy for a very, very long time. And last but not least, I'd like to thank my fiance. So she's my she's my partner, soulmate, and also she's the person who I always ask for advice whenever I have to make any like life decisions, such as like what should we get for lunch, or more serious questions such as like which job offer should I take. And I really appreciate that support throughout like the entire process. And we took so many pictures together, but I would like to focus the one in the center. So the photo in the center is taken immediately after when Korea beat Portugal in the 2022 World Cup and proceed to the round of 16. And I really believe that that was one of the happiest day in my life. And then I am just grateful that I always have someone next to me who can share those happiest memories. And I really look forward to the future memories that are yet to come in the future. So with that, I'd like to conclude my presentation today. And thank you so much. And I'm open to any questions.
Who wants to go first? We use the microphone just for the people.
Yeah, fascinating work. I love it. Thank you so much for the talk. Could you go back to the part 4, the last part of your research?
Mm-hmm.
Yeah, I think you briefly mentioned about the physical model. You incorporated, I mean, you integrated that physical model into your own model.
Mm-hmm.
And I was wondering if you could explain a little bit in detail about that physical model you mentioned.
I see. So yeah, so the question was about, I mentioned that I incorporated some sort of physical model for to represent a sliding between the gripper and the object. But I really haven't had a chance to explain it, but I think it's a good opportunity to explain what that model is. So yeah, so in order to come up with some useful physical model when there is an intrinsic contact and extrinsic contact, we need a model for both of those contacts. And for the extrinsic contact, we just considered a point contact, so therefore we only used a very standard Coulomb friction model. However, what's more tricky is actually the modeling the intrinsic sliding on the intrinsic contact. And in order to represent that, I use a model called the limit surface model. So I actually have a slide for that, so maybe I can use that. Yeah, so this is the limit surface model. And the limit surface model is a very common model that we often use for the planar sliding or planar pushing. So for example, when you have a gripper and then you're grasping something, then there's going to be force and torques exerted at that interface. And we can actually, assuming it's all planar, we can represent the wrench exerted between the gripper and the object onto this 3-dimensional space, because we have 2 components for the translational force and 1 component for the rotational torque. So we can draw a set of feasible wrench that we can exert between gripper and the object. And then if we draw that surface, then it's going to have some boundaries. And that boundary is called the limit surface. So what limit surface implies is that when the exerted wrench is inside the limit surface, then the contact maintains stable. Contact doesn't slip. However, when it actually slips, then the wrench actually lies at the boundary of this limit surface. And what's cool about this limit surface is that, of course, we can exactly know how it looks like, but one way to approximate this limit surface is approximating as an ellipsoid. So if we have this ellipsoid, and then if we have some, let's assume that we have a certain direction that the object is sliding, and then we can also represent the sliding direction also on this 3D space. And then there's a principle called the maximum energy dissipation principle. And following that principle, what happens is that the direction of this slide is going to be orthogonal. It's going to be normal to the surface, to the local surface where it lies. So therefore, in other words, we can get a mapping. We can get a mapping between the direction of the slide and also the wrench exerted. So in other words, if we show you what's the wrench, then you can infer what is going to be the sliding direction. And vice versa, if I give you sliding direction, then you can know what is the wrench. So this model is what I used. And then actually, if we just do some math, and then and then we can come up with this like closed form solution. So for example, so by the way, so G is the gripper pose and the O is the object pose. So we can come up with some closed form solution that given the previous gripper pose and object pose and the next gripper pose, we can predict what's going to be the next object pose. So, and then we can formulate this equation as a factor. So we can just take like OI star minus F as a loss term, and then we can impose it as a factor. So that's how I incorporate this limit surface model into my formulation.
Thank you. Yeah, that makes sense. And then I have one quick question about the part 3. Were there any like limitation in terms of the estimation? For example, like number of contexts, those kind of thing. Were there any limitation?
So yeah, there is limitation. And I think the limitation is that as I mentioned at the conclusion, I do all these things in a very structured environment. So therefore, it can only handle very structured contexts, such as 1-point contact and 2-point contact, which forms a line, and also 3-point contact, which forms a patch. However, when we have some sort of unstructuredness, so for example, if we have some very like rugged environment, and then the contact formation becomes very difficult, then in that case, it's gonna have limitation in solving those problems.
I see. Thank you so much.
Hi, Sangwoon. Thanks for the presentation. So one thing I found interesting was most model-based people go from MPC to RL, but for you, it was the other way around, right? The first 2 talks were doing RL, and then you're doing MPC now. I was curious about the motivations behind that.
So I think I would say the main motivation for that is, I mean, you said most people start with MPC and then move on to RL, but I think the entrance boundary is actually quite lower in the reinforcement learning because you just feed in the data and then you just can get the action. So actually, to me, it was quite natural that I started with the reinforcement learning because we wanted to know like whether this is useful. And then one very efficient and easy way to figure that out was using reinforcement learning. So I would say that's one motivation. And another motivation that comes to mind is I mentioned the challenge of interpretability. So we have input as very high dimensional tactile image. And usually like those kind of high dimensional images are really, I mean, not really hard, but like it's kind of tricky to interpret how to use it. So I thought the learning-based approach would be a good approach to leverage those information that we have. Yeah, so that was the motivation.
Thank you.
Thank you for the great talk. I have a question about dealing with the tactile measurements. I think for visual tactile sensors, those are images which are a lot higher dimensional than like joint positions, for example. I suppose I have 2 questions. The first one is what is the frequency at which you are running the feedback loop? And the second question is if you have found it necessary to do non-trivial pre-processing on the tactile measurements so that you can run the loop fast enough.
Yeah, so actually, so you pointed out 2 points. So one point is like how fast is the frequency of the tactile images, and the second part is can we use some pre-processing to make it faster? And actually, yeah, to come straight to the answer. So actually, the frequency is about like 30 to 50 hertz. And actually, so I think your question is maybe also implying how can we make this algorithm faster? How can we make the motion faster? But what I actually realized is that the speed can be seen from 2 perspectives. So one perspective is one you mentioned, how fast can we run the computation? And the another aspect is how fast can we run the motion? And those two are not necessarily the same. So I'm not sure whether, I mean, maybe I'm pretty sure you checked out the diffusion policy. And then if you see the diffusion policy, they don't run a computation like every millisecond. So they run computation like every I'm not sure about 1 or 2 seconds, and they just follow the trajectory until waiting for the next update. So I'd like to point that out first, and then I would like to talk about the first perspective first, which you asked about how fast is the computation. And actually, the bottleneck for the computation is actually for the not processing the images, but actually it was because it was for running the belief propagation algorithm in the discrete post-factor graph. So so the speed of the discrete belief propagation is heavily dependent on the size of the grid, and that's why we cannot increase the size of the grid infinitesimally, infinite, so that we have like very fine grids. So and then so we actually choose somewhere around like 2,000 to 5,000 grid size, and then with that size, it was able to run the computation every 2 to 5 seconds. However, as I mentioned, it doesn't necessarily mean that acts as a bottleneck for running the motion. Actually, when it comes to running the motion, the bottleneck that we were able to identify was actually the hardware latency between when you actually excite the tactile sensor until when you receive that image on your computer. So it turns out that from our preliminary experiments, it turns out that latency was about 50 to 100 milliseconds. And of course, I mean, I'm pretty sure that if we can do some engineering, then we can definitely optimize that. But at this current stage, it was about that range. And if you think about it, that is quite large, because if we want our motion to run in 1 meter per second, then the 100 millisecond of latency is going to be correspond to about like 10 centimeters of gap between when the event actually happened to when you receive it in your computer. So, and that's large because we're considering like 1 or 2 millimeter accuracy and even sub-millimeter accuracy. So, so that was the bottleneck for speed for running the motion. So I'm not sure. I mean, I think I just answer a little bit tangential, but I'm not sure whether that answered the question.
Yeah, I think that's a lot of useful details.
Okay, great.
Thank you.
That was a great talk. I just had a couple quick questions. One is on slide 24 in part 2.
Just 1 second. You said 24?
24, slide 24.
Mm-hmm.
Right, so on this problem, do you think there's a heuristic where the machine just sees the hole and then just arranges the block, puts it in directly without even thinking about tactile feedback? For this problem specifically?
Yeah, so for this specific problem, as you mentioned, if we use a external vision from the external camera, then yeah, of course, the problem is going to be very easier. However, one point that I would like to point out is that even when you have a vision, it isn't that accurate. So it's that accurate that you can directly insert the object into the hole. So the clearance that we used was about like 0.5 milliseconds. However, usually the accuracy of the vision, if we want to use vision as a prior, the accuracy is like higher than level. So therefore, even though we have, especially if you don't know how the object looks like in prior. So considering that, even though if you have a vision, you might still have to deal with like some trials and errors.
Oh, I see. And the second question is, right, recently there's been a lot of advancements in large language models, so computers can think more and more like humans. Now, if there's more advancements also in tactile sensing, then computers can manipulate their environments more and more like humans. So now, if these things continue to get better, do you see some like major implication for society? You know, some good, maybe some also a little risky.
Oh, that's a hard one. So, yeah, of course, Yeah, of course, like, I mean, I think it really depends on like who is going to use it. And then also like what system are we going to create regarding regulating those kind of things. So yeah, I mean, I think as engineer, I think the engineer's role is to create, like push as much as possible. And as important to that, like as you pointed out, it's really important to set up a very appropriate like system and also appropriate guideline to regulate those algorithms to be used only for the good for the human.
All right, thank you very much.
How's it going?
Going good?
Great talk. Could you go back to the slide where you were training for the policy with you had the shapes that were intersecting and finding the line contacts?
Sure.
Yes. So I guess my question is, I mean, it seemed at least from those examples that there were unique solutions for what the line contact would be, where you wouldn't have to distinguish between whether or not it actually, like, for instance, in that example specifically, right, like the boundaries of the insertion rectangle are such that like the corners don't intersect on the other end, so it doesn't result in planar contact. Or like where you have to look at the other edges. Like, how do you consider those possibilities when you did that training, or did you only provide unique scenarios? And like, is that the sort of thing, like, did those situations appear when you were performing the actual insertions?
Yeah, so I think the question is about how do I handle if there's no possible contact line? Is that the correct interpretation?
Yeah, no possible contact line, or it's like the one that would be shown here is like not the actual one, where you know it'd actually be contacting at like the corresponding contact line would actually be at the boundary of the insertion shape.
Yeah. So yeah, that is actually a really good point, because there are some scenarios where you actually don't get any contact line, or actually the actual contact line is different from the contact line, and that happens when there's more than one potential contact line. And actually, yeah, I considered that during the training. So if it doesn't find any contact line, then I indicate that with a separate variable. And then if there is more than two potential contact line, then I just randomly sample between those two so that it works as some sort of domain randomization. Yeah,
that makes sense. Cool.
Hey, great presentation. How robust is the algorithm that you've developed for increasing the number of contacts? For example, if you had a gripper that was more anthropomorphic, and you had these sensors on every single digit, even the palm, how could we apply that algorithm in that case?
I think that's a very important question, because these days people are coming up with more dexterous hands. And I mean, of course, that doesn't necessarily mean that parallel jaw gripper is going to be extinct, but yeah, that's the problem that we definitely need to think. So I think in order to extend these kind of algorithm to those kind of dexterous hands, I think there are several bottlenecks that I can think of. So for example, one of the major bottlenecks would be modeling those complex interactions with like multiple fingers. And I believe that bottleneck is quite critical when we want to solve that with some like model-based approach. So I think that's like in that case, so that's why the people are using learning-based method in those kind of scenarios. And I also kind of agree with that approach. So in those kind of scenario, it would be beneficial to incorporate some learning-based component to reason about those complex interactions.
Great, thank you. And I'd like to move forward to the next stage on the defense. And I'd like to ask the committee whether you prefer to ask questions in the closed door or open door. Close? Okay, cool. So if everyone please can step out and we'll invite everyone back in a little bit. We should stop the video. Yeah, we should stop recording.